In this video, we are going to be doing Chapter 11, number 27. A space station is constructed in the shape of a hollow ring of mass 5 times 10 to the 4th kilograms. Members of the crew walk on a deck formed by the inner surface of the outer cylindrical wall of the ring with radius 100 meters. At rest when constructed, the ring is rotated about its axis so that the people inside experience an effective free fall acceleration equal to g. The rotation is achieved by firing 2 small rockets attached tangentially to opposite points on the outside ring. So, rocket, rocket. A. What angular momentum does the space station acquire? How long must the rockets be fired if each exerts a thrust of 125 newtons? Prove that the total torque on the ring multiplied by the time interval found in Part B is equal to the change in the angular momentum found in Part A. This equality represents the angular impulse angular momentum theorem. So if you recall from the impulse momentum theorem from the momentum chapter, impulse is the force times the time, and that is equal to the change in momentum. So same thing here. The change in torque times time will be equal to the change in angular momentum. So the first part of the question asks us, what angular momentum does the space station acquire? So to do that, we'll need to use the formula L equals I omega. Let's start by figuring out what the moment of inertia is. We know it's a hollow ring, so I equals mr squared. M is 5 times 10 to the 4th, R is 100. So we end up with 5 times 10 to the 8th for the moment of inertia. Now we also have to figure out what the angular speed of the system is, and that's actually pretty easy to figure out. We know we want the centripetal component of the acceleration equal to 9.8 meters per second squared. Let me just go back for a sec. So this thing is spinning, so the people inside should feel an acceleration of 9.8 meters per second squared. So it's going at a constant speed when they're spinning around. So we want the centripetal acceleration to equal 9.8. From chapter 10, you should know that r times omega squared is equal to the centripetal acceleration, and you can just solve that through for omega. You should get 0.313 radians per second. Angular momentum is I times omega, so you just plug in the numbers, and you should get 1.57 times 10 to the 8th kilograms times meters per second. Okay, so part B asks us, how long will it take for the 2 rockets to get it up to that acceleration? So the first thing we need to do is figure out some expressions here. So the angular acceleration is going to equal the final angular speed minus the initial angular speed minus the time. So we can assume that the space station starts out not spinning at all. So it starts out with an angular speed of 0. And the final angular speed is the omega that we found in part A. So the time is going to be equal to omega over alpha. Now the torque is going to equal the force from each rocket times the distance from the center. So what we're doing now is we're trying to figure out what alpha is. Or we're just trying to figure out the torque, my bad. So the torque, there's 2 rockets, so that's where the 2 comes from. And then each rocket is exerting this force, and each rocket is this distance from the center. So that is the torque being exerted on the ship. Okay, so we are trying to find alpha. I was correct when I said that before. Aren't I smart? Okay, so torque is equal to the moment of inertia times alpha. If you solve that for alpha, you'll get torque divided by moment of inertia. We just figured out our torque, And we got our moment of inertia from part A of the problem, so we just plug in those numbers. And we get 5 times 10 to the negative fifth radians per second squared. So then we plug in 0.313 for omega and 5 times 10 to the negative fifth for alpha, and we get that the time is equal to 6,260 seconds. So that is our answer to part B. Okay, we still have to do part C. So remember, for linear momentum, this is what the impulse momentum theorem is. And for angular stuff, this is what the formula is. So torque times time equals the change in angular momentum. So the torque times the time is going to be 25,000 times 6,260, and you get 1.565 times 10 to the 8th. And I would like to point out that 1.565 times 10 to the 8th is almost exactly equal to this number, which is the change in angular momentum. So we have just proved the angular impulse, angular momentum theory.